lesson full of definitions. So get ready with your paper, pencil. If you don't have this stuff written down as notes, it's going to be extremely more difficult than it needs to be. So go ahead and take a minute and get your stuff ready if you're not already. Morning, Aaron. Morning, Maria Celeste.
Good morning.
Good morning. We haven't started yet, but I was just kind of giving the other folks a warning that this is going to be pretty heavy in definitions today, and some diagrams too. And frankly, even to me, who enjoys this stuff, it's going to be much harder than it needs to be if we don't have our notes, a record to look back on. So go ahead and get your stuff ready if you haven't done so already. And then we're going to start in just 30 seconds. So what you did on Tuesday, and then we kind of recapped it yesterday, was work with the circle formula. Now we're going to actually dig into the geometry of circles. So we're not going to be dealing with the formula today, which is nice. We're going to put that to the side. It'll come back again in the future. But we are still sticking with circles and all these different parts of circles. So we're going to be defining various lines and segments that are on circles and various angles on circles. And then this is the big one. We're going to be looking at five theorems using all the different lines and angles that we're going to define first. Here we go. Remember, theorem is like a rule that we can use to help solve different problems, different math problems. So here we go. Good morning, Bailey. All right, everyone, get your stuff ready, get your paper ready. Here we go. And let me go ahead and move this thing for now. So start by drawing yourself a circle. It's okay if it's not perfectly round. And then put the center in it right there in the middle. And we're going to name and define these five terms here: radius, chord, diameter, secant, and tangent. Give yourself lots of space for these definitions. So you can just do the top one for now, radius, and then when that's done, we'll do chord and so forth. Good morning, Keegan. You haven't missed much. We just started, and I haven't even started yet. So get ready, because we're going to define lots of different parts of circles, and then five different theorems or rules that we'll use about these different parts of circles. Okay, so start by drawing yourself a circle. And let's label the middle point, the center point, O. And let's define radius. So this is probably one you're already familiar with. A radius is a line segment that connects the center to any point on the edge of the circle. Line segment connecting or joining the center to any other point on the edge of the circle, or just usually how we say it is on the circle. We don't mean in the middle somewhere, we mean on the edge of the outside. So if I have point A floating on the edge of my circle, if I connect O to A as a straight line segment, that would be a radius. So a line segment connecting the center to any point on the circle. Our radius example so far is OA, segment OA. Okay, so that's the one you've probably used before. Maybe you've used or seen these other ones before too, or maybe not. It's just we might all be on different pages. So let's define them all today together. So a chord is another line segment connecting any 2 points on the circle. So let's say we had point B. Let's put it here. That's a point on the circle, and then point C below it, also on the circle. If I connect BC, this is a chord. So it's any line segment that's like connecting the edges of the circle, but it's not necessarily going through the center. Line segment connecting any 2 points on the circle. And our example right now is segment BC. All right, for diameter, this is actually another one you might have heard or used or remember. Anyone want to share with me and with the group what a diameter is, how you think of it? Does anyone remember what a diameter is?
A straight line, like going from side to side.
Going from side to side.
Am I right?
You're right. I want to be a tad more specific. Look at my line BC, my chord. That's a straight line going from like side to side, isn't it? Like up, down, across the circle. Why,
Yeah.
why isn't BC a diameter? I think you know. Maybe let's just talk it through.
Is it because it's in the middle and it's going
It's
side
got to
to
be in
side?
the middle. Very good. That was Manaya, right?
Yep.
High five, dude. So a diameter is another line segment that goes through the center. It has to go through O, the point in the center. So technically how it's defined is it's a chord that passes through the center. And like Manaya said, it's going all the way across. Okay. It's got to be going right through the middle, the center point. So let's make a diameter here. I'm going to go ahead and just extend OA, the radius we made earlier. And we've used B and C, so this is point D over here. So now our example for our diameter on this circle is AD or DA. You can name it either order when we're naming line segments. So I'm going to say DA, segment DA is a diameter. Perfect. Technically, it's a chord, right? Because it's a segment connecting any 2 points on the circle, D and A, but it's a special chord because it cuts through the center, making it a diameter. Okay, now for the other ones. I hope people are ready for me to cover up the stuff on top. I'm going to move this up here, and if you need me to move it back down, just please tell me. So secant is the next one. That's how we say that. Secant. Secant. A secant is a line that intersects the circle in two places. A line that intersects the circle in two places or 2 points. Now, you might be thinking, well, isn't BC intersecting in 2 points and DA intersecting the circle in 2 points? Yes, they are, but they're not lines that go on forever. They are segments cut off at their endpoints. So to show a secant, I'm going to make a line that's cutting straight through, like so, coming from outside the circle, crossing through, boom, and then continuing outside. And let's see, we're up to E and F. So E and point F right here is our secant on our example. And this is not a segment, so when I name it with my symbols, I'm going to put little arrows on the symbol for EF because it's a line. It is also a segment between E and F, but it is also a line because it goes on forever. So line EF is a secant. Okay, and our last one is tangent. A tangent is a line that intersects the circle at only one point. Let me write that, and then I'll draw a picture. A line that intersects the circle at only one point. So what does that look like? A line that intersects at only one point, it only is grazing the outside. So for example, if I had a point G somewhere on my circle and a line that's outside the circle, like so, it's like touching it, but it's just barely. It's only intersecting at point G. And I have to have another point on here. So let's put H on that tangent line and call it line GH. Is a tangent line. Okay, that's it for our line segments and lines that we need to be familiar with. So next up, we're going to look at angles that are, found in a circle when we have all these different line segments. I'll wait a little bit. Does anyone need the top of the screen again?
No, I just need the bottom.
Okay. Anyone else? Do me a favor. Since we're writing a lot, I want to hear from all of you when you're ready to move on. So in the chat, tell me when you're good and you're done with this screen. Or tell me if you have any questions. And we'll move on once I hear from each of you that you're done with the screen.
Can you move it down a little bit so that we can see the full definition of tangent? I said that so wrong.
I don't understand. So in the past, you've said, Manaya, that you can't see the bottom of my screen, but other people I think can. Are other people having trouble with tangent? Can you see it all, or is it cut off?
It's cut off.
It's cut off. Who's that?
Delaney.
I could see it all.
You can see where it says GH is a tangent, this little tiny sentence at the
Yeah.
end? Okay.
Yeah, I can see that.
I wonder
I
why,
can see it as well.
Maria, Delaney and Manaya, what kind of, are you you guys aren't on your phones, right? You're on a computer, a Chromebook?
Yeah, I'm on the school computer.
I'm on a Chromebook from the school.
I don't understand why it's cut off. Is it cut off? Do you have like a, what am I trying to say? The little taskbar with like different apps and stuff? Is that what's in the way?
No,
part that says chat and participants and share and view
Yeah.
and share video.
Okay, I'm sorry. Let me see if I can like zoom this thing out. I want to zoom out. I'm sorry. Rats.
Wait, I figured it out. You have to move your mouse off of the chat thing, like where it's chat mute and stop video. You have to stop. You have to move it off of the thing. You have to like move it somewhere else, so then it'll show you the full screen.
So I need to move mine?
No, whoever can't see it.
Okay. So you moved your mouse. Can you describe to Delaney and maybe anyone else who's still missing it?
I just
Manaya?
moved my mouse off the Zoom call and then it went back to normal.
Delaney, can you try that too?
Yeah, it's not moving. Do you mind just telling me what it says when it, like by the arrow?
Of course. So for tangent, the definition is it's a line that intersects the circle at only one point. And then after that, I just wrote a tiny thing saying it about our example. I said GH is a tangent. Can you see the drawing of GH, or is that cut off as well?
All I see is a line that intersects the circle at only one point, and then I see that little arrow that goes from side to side, and then I don't see anything
Okay,
else.
so the little arrow is underneath that is GH, and that's describing like the picture of point G, point H, the line going through them. So it says GH is a tangent line. And that's it.
Thank you.
Thank you. Thank you for your patience. And Manaya, thanks for figuring out that thing about the mouse. And Delaney, I'm sorry it's still cut off. I'm not sure how to fix it. So I'll look into that this weekend. Okay, Braden, you're good. Keegan, you're good. Aaron, thank you. Manaya. Andrew? And Bailey? Are you guys still copying, writing down, copying? Okay. Bailey, how about you? You there, Bailey? Okay. Let's look at the angles now, guys. And good news is I'm going to try to just keep my writing above like the very bottom of the screen. So let me know again if it's cut off. Start again with another circle, a clean one. Let's name the center O again. And we've got to look at these different four angles and things that have to do with angles. So a central angle, let's start with the one at the top. This is an angle whose vertex is at the center of the circle. An angle whose vertex is at the center. Also, it's worth pointing out that the sides of this angle are radii. So I'm going to add that next. The sides are radii. That just means two radius. Radii. The sides are radii. Okay, so let's see what that looks like. If I've got two radii, so let's do point A up top and connect it down and make a radius, OA. And we have another point right here, B. Connect that. So we've got two radii, or two radiuses, OA and OB. This angle between those two radii we just made, that's the central angle, AOB. So I'm going to put that above in purple again next to the definition. As an example, angle AOB is a central angle. These are our favorite because they are right in the middle. Another thing is that, actually, I'm going to wait on that. We'll look at that in another screen. So that's it for central angle. Now for arc. An arc is not an angle. It's a section of the circle. I'm going to define it like this. A portion of the circle So for example, let me change my color here. This edge of the circle, the curved edge between A and B, is an arc. And how we name them with our symbols and how you're going to see it in Inmentum is the 2 points that connect the arc. And then instead of like a line or a straight line or a segment on top, it's going to be a curve, kind of like the edge of the circle. Arc AB, that's how we say that symbol. Arc AB is an arc. It's a little... let's look at another one. I'm going to put point C on here. And we could also describe more arcs now. We have arc BC, connecting B to C. Or we could look at the bigger one, arc AC, all the way from A to B to C. Or if we wanted to describe the other side that I haven't colored on yet, the black side from A all the way around, we can still call that an arc. Let's go ahead and do that. I'm going to make a point here, D, at the bottom. So if you want to describe the larger arc, you have to use 3 letters. So to distinguish between the smaller arcs. So if I wanted to look at from A to C on the other side, though, I would call that arc ADC. So this is also an arc. There's many more here that I haven't listed, like BC or BD, arc. Arc BC, arc BD. But anyways, there's 2 examples. So the arcs are not angles, okay? Arcs are the actual edge of the circle. And here's one more thing I'm going to add to our definition on the left under arc. The measure of an arc is equal to its central angle. So, for example, let's say we were looking at the central angle again, AOB. Let's say we knew this angle measure inside that circle was, let's say it was 45 degrees. That's this angle right here, AOB. The corresponding arc to that is the arc of the circle on the outside that's being cut by those rays, by OA and OB. So therefore, arc AB, this is also described as 45 degrees. So if the central angle, if we know that is 45 or something, any number, then we know its corresponding arcs measure as well. So in my example here, arc AB is 45 degrees because that central angle that's also intercepting AB is 45 degrees. Before we look at any more, any questions? I see something in the chat. Oh, it's all good, Antonio. You did miss the first page though, so make sure to look back at those notes later. Any questions, folks, about central angles or arcs right now? Naming them? Anything?
No.
Okay, thank you, Aaron. Okay, let's look at an inscribed angle. The name inscribed is kind of nice. It's a little clue as to what it means. It has this prefix of in. So an inscribed angle, an angle whose vertex lies on the circle's edge. Let's make a new one here so it's not busying up our purple angle. I'm going to put a new point, E, on the left, and that's going to be our vertex for this inscribed angle. So E connecting to C, that's a chord. E connecting to D, that's another chord, a smaller one. And the angle CED, right here, that is an inscribed angle. An angle whose vertex lies on the circle's edge. And also just note the sides of an inscribed angle are chords, not radius, right? Because they're not from the center going to the edge. They're just kind of random lines cut through the circle itself. I'm going to add that in here. The sides are chords. And then for our example, I'm going to put that above it here just for space. I'm going to say angle CED is an inscribed angle. And now I'm going to do the circumscribed definition above it in purple, just because of the cutting off of the screen business. So for circumscribed angle, this is an angle whose vertex is outside of the circle. Circumscribed is an angle whose vertex is outside the circle. And these circumscribed angles, their sides are tangents. The sides are tangents. Remember, tangents are lines that are outside the circle, touching in just one, or intersecting in just one point. So let's put this on our diagram now. And I realize my circle's kind of big and I maybe should have made it smaller. So the vertex is outside. So I'm going to make a point F outside here. And now I'm going to draw two tangents to the circle from F. So I'm going to try my best to make it a straight line that's grazing the outside of the circle without crossing through twice, just once on the edge. Here we go. Okay, pretend my line is perfectly straight. There we go. That's a tangent. And then another one below. And I'm going to go ahead and add some points of tangency in there where that circumscribed angle is grazing the circle. So let's see, we're up to G and H again, I believe. So let's say we have point G here and point H at the bottom. So for our example, we can say, I'm going to state this on the left, angle GFH is circumscribed. So we've got central angles, and that kind of tells us central, middle. Those have vertices at the center, like AOB. We've got inscribed angles so their vertices are right on the circle's edge, and it's an inside angle inside of the circle. And then we can have circumscribed, and that means it's outside the circle, like GFH. Okay. Do me a favor, please. Chat when you're good, or if you need more time. Chat me when you're good, and then I'm going to move on when all of you have said you're good to go, no more needing to copy. I don't mean to rush anybody. I just don't want to leave anyone behind either. So we can hold up a sec while people are still writing. What we're going to do next is look at 5 different theorems that put all these ideas to use. So there's no more like straight up definitions left, but we are going to see some different like results that emerge when you start looking at the angles and all the segments together. And I see 3 of you have chatted. Thank you. If there's anyone else who has a question, or if you can't read my writing, please tell me. If you need any clarification, I'd like to do that with you now before we move on. Okay. Thanks you for. I think there's still 4 more of you, so I'm going to wait. It's all good. If we don't get to all 5 theorems today, we'll just cut it there and pick up next week. Okay, there's 2 more of you. Maria Celeste and Antonio. Okay, thank you. Awesome, Braden. Thank you. And let's see. I think that's everybody. All right, here we go. Theorem 1. Theorem 1. The radius of a circle is perpendicular to the tangent. So please copy this down. The radius of a circle is perpendicular to the tangent. Perpendicular. You know this. It means 2 lines are crossing, and they're crossing at a 90-degree angle, or at least they're meeting at a 90-degree angle. Perpendicular means 90 degrees or a right angle. Now you know what tangent means. That's a line that's outside of the circle, it cutting through just at one point, right on the edge. So let's draw a diagram of this theorem. We have our circle. We have a radius. We know how to draw a radius. And if you have a tangent meeting right there at that radius, the theorem is saying that these 2 lines are meeting at a 90-degree angle. I'm going to put in the 90 degrees in with that little symbol of a box in the corner. And maybe I did this backwards. I'll fix that for the next examples. Let's label our circle as well. So the center we'll call O again. Let's call point A, where it's the radius is meeting. And then on the tangent line on the top and bottom, I'm going to name that B and C. So we can say, because of this theorem, that segment OA, or radius OA, is perpendicular to BC. To line BC. That's how we say what I wrote in symbols above. Segment OA is perpendicular to line BC. This works when it's a radius and if it's a tangent line. So not for the other ones, right? Not for a chord, because a chord could be at some weird angle, and not for the secant lines, because those are cutting through at weird angles. Only for the tangent and the radius together. Okay, I want to show you an example of theorem 1 now. If you don't want to put this in your notes, it's okay. If you want to just follow along and try to solve it with me, that's okay. I do want you to have the actual theorems, though, that we just did. So example 1, let's look at the picture. We've got a circle, we've got the center O, we've got 2 points on the circle labeled B and D, and we see on the outside a line that looks like a tangent circle or tangent line, BC. How do we know this is a tangent? Because it's intercepting the circle at point B and nowhere else. This straight line BC looks tangent because it's cutting through right at B, and that's it. It's intersecting at one place. We also have kind of a partial secant, CO, that is cutting right into the circle. That's certainly not a tangent. Oh, also, angles. I see a central angle, BOD. So that might be important. Now let's look at the words. In the figure, BC is tangent to circle O. Measure of angle, BCO, that little m, that means measure. And the symbol here means angle. The measure of angle BCO is 28 degrees. So let's mark that on our picture, BCO. So where those two lines are meeting, that's the angle we're describing, right at C. It's always going to be the middle letter from the name, BCO, C. That's the corner where you're going to mark it. So this is 28 degrees right here, based on the words. They want us to find the measure of arc BD. They want us to say, what is this arc's measure from B to D, this edge of the circle? Now, we know from earlier that the measure of the arc, BD, that will be equal to the measure of angle, BOD. So if we could know this angle, this angle's measure, then we could have the arc, BD, because they're equal. The measure of BD arc is the same as that central angle. Do you see the triangle being formed in this diagram? We were given angle BCO as 28 degrees, and we see an angle right here where the radius OB is intersecting tangent BC. So there's a triangle BCO. Remember from, all your other math classes that you've done, all triangles, interior angles add up to the same number. Whenever you have a triangle, the 3 angles inside add up to a special number. And if we could figure out what the angle at OBC is, then that would lead us to the central angle, which would lead us to the arc BD's measure. So, can anyone tell me down here where I'm drawing in purple in the left of the screen? Just a side example question. Does anyone remember what the number is, the measure is that all triangles' interior angles add up to? Their sum? A certain degree number. Okay. Totally. Antonio, high five to you. It's 180. I know you've all heard that a million times, so we have to refamiliarize ourselves with that. All triangles add up to 180. So for back to our actual problem or question here, 28 degrees plus the angle at B plus the central angle at O, those all add up to 180. I'm going to write that down here on the right side. I'm going to say it like this, just to make it a little cleaner, even though I'm kind of cheating a bit with how I'm naming these. Angle C plus the angle at B plus the angle at O, the central angle. These all add to 180. And we know one of them is 28, so I'm going to plug that in. That theorem we just did, theorem 1, says that the radius meets the tangent at a 90-degree angle. They're perpendicular. So that means we know angle B now. That means angle B right here, this is actually a 90-degree angle, a right angle. So I'm going to plug 90 in for angle B. 28 plus 90 plus the central angle O is 180. And now we can solve this equation for angle O, the measure of the central angle, and that will tell us what the arc BD's measure is. So if we subtract 90 from both sides, and if we subtract 28 from both sides, that'll tell us the central angle and therefore the arc BD. So after subtracting, we get angle O is 62 degrees. So that means inside here, that's 62. That means the arc BD is also 62. The measure of arc BD is 62 degrees. So we needed that theorem that told us that that angle B is basically a 90-degree angle. We needed to remember the arc measure is equal to the central angle measure that intercepts that arc. And then we had to put that together with our knowledge of all triangles add up to 180 degrees. And since we kind of have a triangle forming here, we could use that as well. Okay, if you didn't take notes on this, that's okay, but take a picture really quick so you have this to look at for later. And then we're going to move on to theorem 2. We're not going to finish all 5 today. I figured that out finally, but we'll see how far we get, and we're going to stop. I want to see your notes for today as your participation and your attendance, okay? And basically your homework. We don't have enough to do the mastery test today. So at the end of the lesson, I'm going to ask to see your guys' notes, just a heads up. All right, here we go. Let's look at theorem 2. Theorem 2. The measure of an inscribed angle is half the measure of the corresponding central angle. Is half of the corresponding central angle. Go ahead and write that down, and then let's draw a diagram together of this theorem. So remember, inscribed angle means its vertex is on the edge of the circle. Central angle, you know, the vertex is in the very center. So what do they mean by corresponding? Let's draw, I want to start like this. Let's label our circle point 0 in the center, or O rather, in the center. And I'm going to go ahead and make it going upwards this time for our example. I'm going to draw a central angle. So let's draw OA. And then to the right, we'll draw OB. So we've got central angle AOB drawn. And now I want to draw an inscribed angle that is using the same points A and B. Before you draw, let me try to show you what I mean. I'm going to make a point C over here on the left. It could be anywhere, but I'm just going to put it there for my picture today. And now if we connect C to A, straight line as best you can, and C to B. Oh dear, there we go. So now we have two angles shown in this diagram. We've got angle ACB and angle AOB. The purple one, AOB, is central. The red one is an inscribed angle. And theorem 2 is telling us that we can figure out the measure of one or the other if we know one of these angles. It's saying that the inscribed angle is half of the central angle's measure, as long as they're intercepting the same points, A and B, like this picture is. So for my diagram, I'm going to state the theorem with symbols now. Measure of angle ACB, that's the inscribed, is equal to half of measure of AOB. Angle AOB. This is my inscribed is equal to half the corresponding central angle. So let's just say we knew AOB. Let's say we knew that that had a measure of 50 degrees. So if AOB was 50 degrees, and I wanted to find the inscribed angle measure ACB, I can plug them into this formula we've created from this theorem. So the measure of angle ACB, that's the inscribed, is half of the central AOB, and we know that is 50. So half times 50, 50 divided by 2, that means the inscribed angle is 25 degrees. And this only works if both angles, the central and the inscribed, are using the same points of intersection with the circle, A and B. So if the inscribed angle is going in a different direction and not intersecting A and B, then it's not going to work to use that central angle. They have to be using the same spots, A and B. All right, we're going to do one more example using theorem 2, and then we're going to go for the day. But before you go, I want to see your notes that you take, and just so that you have something from what we've been doing. Hopefully everything. I'm going to move on. If anyone needs more time, please let me know. So let's try an example using this inscribed angle rule. Okay, if the measure of angle ABC is 70 degrees, what is the measure of AOC? And I've already marked it. A to B to C. So this whole spread right here is 70. And they're asking what is A to O to C. They're asking for this larger looking angle right here. That's AOC. Okay, so notice that AOC, oh, someone in the chat. Okay, Antonio, that's fine. You can send me your notes when you're done. Share them with me if it's on Google. Just type in my name under share and it'll pop up. Josiah Henderson. Or you can download them and email them, whatever's easiest for you. So let's see here. Notice that AOC is central. So here's just some ideas and notes here. Angle AOC is central angle. The green one, well, the one on top, that's 70, that's an inscribed angle. So angle ABC is inscribed. Let's go to our theorem 2, which says that the inscribed is equal to half the central if they're intercepting the same locations. And are they? Let's double check. Angle ABC is supposed to be on the line to right here at A. So it's using BA and hitting at BC. Okay. And so is the central angle. It's using these two radii, OA and OC, like so. We're not really using that radius, the black one that I didn't draw. I don't think we even really need that. Sometimes your problems will have information in it that we don't actually even need to use. And I don't think we need this line segment or the triangles that it's created. We're only interested in what I've highlighted there. We know one of those measures. The inscribed one is 70 in this case. And that's equal to half of the central, which is the one they're asking about, AOC. So instead of dividing 70 by 2, we need to actually multiply both sides by 2 to clear out that fraction. So 2 times 70 is 135, I think. No, it's 140. I can't do math. Nice. So 2 times 70 is 140. And then on the right, 2 over 2 is gone. And that's our central angle, measure of angle AOC. So we only needed to use that one theorem in this case and be able to identify the parts and plug the right numbers into the theorem, into the equation. All right, we're going to stop there for today. We got through 2 theorems on Tuesday morning. Just a reminder, I'm going to send out an email and a text on Remind, but there's no class on Monday. We're closed, so there's no meetings with your teachers or any classes with me or Jules on Monday for President's Day. We'll also be gone tomorrow on Friday. So I'll see you guys again on Tuesday, and we're going to pick up right away at Theorem 3. We're not going to start by reviewing all this stuff. We're going to do Theorem 3, 4, and 5, and then some examples.
Sorry.
Yes.
Can you go back to Theorem 1 real quick? I just need it ready.
Absolutely. I'm going to go back to Theorem 1, and then I'm going to pause and look at everyone's notes, please.
Okay, I'm done.
Okay. All right, cool. If anyone wants to see another page, please let me know. Otherwise, I'm going to pull up this. And if you guys could just show me your notes that you have something for today, you're good to go.
I typed mine.
Okay, then you need to send them to me just like Antonio said. Thanks, Aaron. Got it. Appreciate it. Aaron's good.
All right, have a good weekend.
Okay, you too, Aaron. You take care. Delaney, thank you. Thanks for working hard, even though it was cut off, Delaney. Good job.
Bye.
Bye. And Antonio, you can just send me yours if you want to. Keegan, appreciate it. Good job. Thank you. And Maria, I got you. Thank you. Maria, did you get any diagrams? Do you want to go back and see those again? Okay, you're good? Okay. Just checking. Thank you. All right. So Andrew, Bailey, if you can hear me, I'm not sure. If you want to just watch the video again later, you can always do that. And then you can send me your notes later. If you're typing them, send me what you got.
I got screenshots.
You do have screenshots. Awesome. Can you send me some of those so I see you've got them for later?
Yes, I can go back a few slides.
Oh, go back right now?
Yeah.
Yeah. Do you know which slide you would like to see?
I forgot which slide it was.
We started with
Yeah, that one.
This
That
one.
one.
Totally. Okay.
Then the next one, and that's it.
Sure. Okay, my clock says 11, so I've got to let you guys go. This afternoon, I'll have the video up if you want to see that again, and the slide as well. You can just look at the slides.
I sent them to your Google chat.
Beautiful. Thanks, sir. Have a great weekend, okay?